Okay, thanks, Frank. All right, so I will present experimental results from the LHC. And of course, it's a enormous task if you want to cover all of the results. I guess many of you saw this particular figure, which shows range of the cross-section measurements at the LHC. So this is a plot from Atlas, but there is a similar one from CMS. And you cover a huge range from total cross-section to very rare processes. And of course, and each of these tests is a very interesting measurement by itself, and with very many ingenious experimental challenges and solutions to them. I would love to talk to you about many of them, but you have to make a choice. So the idea, I will select just Draellian measurements, which will be WZ production. A little bit I will talk about jets, I guess, tomorrow, and TT bar. And the focus here will be on the precision tests of the standard model. So basically, if we so the motivation here is it comes essentially from this particular plot. So we have a number of measurements of various sensitive observables, and in the standard model we have a over-constraint of the parameters, and you can, based on the precision measurements of them, predict values of the others. So in particular, if you look at the predictions for the W mass and the top mass, essentially through the electroweak feed to the other observables, you have a rather tight constraint for them. So this is shown as an ellipse. It's a gray ellipse. And the range which is covered by this ellipse is quite narrow. So, and the point here, if we perform the measurement of the same quantities experimentally, would they agree or not? So if you have a disagreement between the W mass predicted from the electroweak feed and the direct measurement, potentially there are some new effects, some additional particles in the loops, and this will be an indication of something going on beyond the standard model. All right, so W mass, if you look at this plot, the W mass is interesting in particular because the theory prediction uncertainty is roughly similar to what we have in the data, so roughly matching each other, so if you do projections. So in case of the top mass, the situation is somewhat different, so the theory uncertainty is quite a bit larger compared to the direct experimental measurement. On the other hand, of course, the top mass is extremely interesting as well because this is the heaviest standard model particle, so it couples to Higgs very strongly, and again, many interesting things may happen here. All right, so okay, so the key point is we want to measure these quantities very precisely to test the standard model, and in fact we can do that at LHC. So this is a summary of the W mass measurement which were performed until recently. So in fact there is additional measurement from LHCb which I haven't added here, but it's also there. So we have the first measurement which comes from lab. Of course, lab mostly operated at the Z resonance, so it was only late runs which were taken afterwards at that higher center of mass energy, and the luminosity was relatively low, so the uncertainty is large even if you combine all the experiments. So then we got a few results from the hadron machine, so from the Tevatron and the Tevatron lab combination. Interestingly enough, actually dominates. This combination is dominated by the Tevatron result, and there was a hint of a tension between the prediction and the experimental result. So if you remember the history of G-2, this type of hint is it was 2 sigma to 2.5, now it's 4 sigma. So there was a hope that something similar will happen here. But okay, with the Atlas measurement, it looks like we are getting closer to the standard model. Okay, so this is one observable. The other observable will be Weinberg angle. So again, so it's here on the other hand, left results are very accurate. So as I said, left operated at the z-pole, so you can have nice statistics there. But yet, Atlas has a LHC in general have very large z-boson samples, so they become competitive. So this is very nice, and you want to improve in future. And I will talk about a little bit about experimental techniques, how to make these measurements more accurate. But at the end, the leading uncertainties come, in fact, from theory, from modeling of this process in the QCD. In particular, for WMAS, the key issues are Barton distribution functions, recoil modeling, and also modeling of the W boson polarization. So this result, which is shown here, is performed at 7 TeV. So there are samples at 8, and of course at 13 TeV will be even larger samples. So statistically, you will get a higher accuracy there. On the other hand, modeling uncertainties will potentially become even worse at 13 TeV. So therefore, we need to do something about it, and we need to constrain them using experimental data. Of course, whatever you heard about modeling of in Monte Carlo and theory in the previous lectures, this is absolutely essential as well. So the combination of the to get this accurate results, the only way to get them is to combine data-driven constraints and physics modeling. All right, so just a very quick recap of what we are talking about. So just a few slides of the Draellian production. So it's the simplest process in the proton-proton collision for the QCD. So we have two partons producing intermediate photon W or Z boson, which decays into a lepton pair. So lepton pair could be a pair of electrons, muons, or taus, or in case of the W, this will be charge current, and so it will be electron and neutrino or muon and neutrino. Okay, so of course, if these are pair of charged leptons, they are rather easy to measure in the detector. So if these are not a tau pair, and in case of the W, the signature will be lepton and the missing energy. Okay, so this is the simplest process in QCD. So it's to colored objects into zero colored object. And yeah, this is well known, well understood, and that leading order is just QQ bar annihilation. Okay, so again, very quickly going over the kinematics. So the key variable will be the invariant mass of the pair, which will be of course in case of the Z production peaking at the Z mass, in case of the W at the W mass. And then of course we have X1 and X2, the momentum fraction, which are carried by the partons participating in the interaction. Okay, at leading order, if we want to produce an S-channel object, so the formula for the invariant mass is just we take a momentum of the parton, the first, second one, the square, and then we get the invariant mass. Okay, the other interesting experimentally observable is the rapidity of the lepton pair. So we take the standard formula to calculate it, substitute X1, X2, and we get to this well-known relation again. So combining these two formulas, we can relate the rapidity of the lepton pair, the mass of the resonance, center of mass energy of the collider, and X1 and X2 of the patterns. So this is actually already interesting, quite interesting information, and we allows us to put LHC experiments together with deep and elastic scattering experiments here and fixed target experiments on the same graph. So yeah, so what you see here, this is actually deep and elastic centric kind of, because it shows you X, single X, and co-square dependence. And yeah, you see kinematic coverage of various experiments. So here covers a wide range in X and co-square. And what is the first message from this plot? You see that the coverage is sufficient such that the X range of the LHC is basically covered for most of the processes of interest, most of the high scale processes. This is a plot for center of mass and energy of 70, but it holds true at 30 TeV, it just moves a little bit to the left. Right. So there are a few more lessons from this plot. So yeah, so the X coverage is of course very important, because if you want to make predictions at LHC, we need pattern distribution functions which are determined PIS, and then you evolve to higher scales. So this is fine. This is all well understood, but of course PDFs themselves are phenomenologically determined functions, and so you can only predict cross-sections for X ranges which are already covered by PDFs. So you cannot predict in the latter direction unless you do some approximations. Okay. The other lesson is that if you are interested in discoveries of things like SUSY or something which is a mass channel at very high scales, you don't need to build a detector which would with very wide coverage. So everything is limited in the rapidities between roughly 2, or if you go even higher scales, it's only a central detector which matters. Okay, this is of course different if you are interested in the things like measurement of the okay, for W and Z, you already want to have a rather wide coverage of the detector, and LHCb is actually quite interesting device in this respect. The other lesson is that if you are interested in these processes at very high scales, you also have to understand PDFs at high X, and what you see here are a few fixed target measurements from NFC VCTMS E665. And SLAC, and some of them are actually from really long time ago. So SLAC measurements are from 70s, VCTMS and NFC from 80s. So these are very nice results, but okay, some of the treatments of the experimental data are maybe perhaps not super modern. It would be actually very nice to have something here, and potentially EIC, the future EP collider, may have here. On the other hand, if you want to build another collider with even higher center of mass energy, we would extend the coverage, PP collider, and we would have to do something about low X. And then there are again proposals to do things like LHC. Okay, so these are side remarks. Let's go back to the Draellian and the LHC measurements. Okay, so let's start with just integrated everything but differential and invariant mass and rapidity, the two most important kinematic variables, leading order double differential cross-section. The formula is very simple. So it contains essentially two terms up to constant. So this is a propagator term and a partonic term. So, all right, so if we talk about neutral current, we have, of course, both photon exchange and Z exchange, and we have an interference between the two. And at the end, we get, yeah, the cross-section is fixed sharply at the Z pole, and of course, it also increases at low scales. It's also interesting to see that the contribution from the interference term is actually quite small, and this is to some extent as an accidental feature because of this smallness of this vector coupling. Just maybe as an exercise, if you can recall what's the value of this parameter in the standard model, which we can discuss in the evening. Right. So the other interesting feature, if you look at these propagated terms, are the couplings. And okay, so for the photon exchange, this will be electric charges, and for the Z, of course, these are the vector maximum couplings of the Z. So similarly, this happens for the structure for the Z decaying into the, so actually for the production term. So this was for the decay, the Z into lepton pair, but also for the quark to Z or photon interaction. This will be a different set of couplings. All right, and this is actually what makes the life kind of interesting from the Parton distribution function that and more difficult in terms of the measurement of the W mass is that we have a rather complex flavor composition of this Z or photon production. So if you look at this as a function of rapidity, we have, in case of Z and gamma, we have contributions from UU, DD, at CC bar, SS bar, and BB bar annihilations, and okay, and all of them are rather sizable. But there is also quite some difference between the Z and photon exchange, because that Z is more coupled to down type quarks compared to the photon, which is so here electric charge plays a role, and so it's more coupled to U quark. Right. Then there are also the funny structures and shape, which are like double humps or single humps. And this comes from the fact that, of course, we have the PP collider, and the protons do contain not only the C quarks, but okay, there are 3 valence quarks, 2 U valence quarks and 1 D valence quark. And of course, if you have UU bars, you sometimes have the valence quark, which would be corresponding to larger X values and therefore a higher rapidity, and therefore this structure, so which is kind of more pronounced for the photon exchange because there are 2 U valence compared to 1 D valence quark. So again, this is okay. So it's actually quite important that we have valence quarks because it brings violation of the symmetry. So so this allows us to measure wider angle, in fact, but it also creates some difficulty for the W mass measurement. Okay, so if you look at the decomposition, flavor decomposition for W plus W minus, so it's kind of similar situation. So in case of W plus, we are sensitive to U D bar, C S bar, assess the main 2 contributions, and then there are additionally suppressed contributions, but they are relatively small. However, for precision measurements, are of course also important. And yeah, so the cross section for W plus is higher compared to W minus, essentially because of the 2 valence quarks for U and 1 valence quarks for D. So the symmetry of the cross section essentially is a measure of the U over D PDFs. And okay, so another important feature here is that CS, so the charm strange production, is actually quite sizable for the W, so definitely not negligible on the W mass scale. And of course, this is so if we talk about UD bar, these are 2 light quarks. So here we talk about a heavy light quark, Modeling of this is more complicated. So transverse momentum, which is produced in this reaction, is different. So it needs to be understood as well. And of course, the strange quark is another object which is quite difficult to constrain, and again needs to be understood if you want to model the W production. So this is a production, but then of course comes the decay, and here again the situation is rather complicated for the W. So we have it's polarized, so we have the A structure of the production and decay, and so if you compare, if you look at the correlation between the rapidity of the W and rapidity of the lepton for W plus and W minus, so there's of course a correlation between the two, but there is also a funny additional structure which is different. So it's just essentially yeah, from the parity violation and the decay, and for example, if you look at in the experiment, you have to select the range in which you measure, so applying cuts on the PT of the lepton and say the rapidity. And if you look at the W rapidity covered, in this case, it's quite different. So it's, again, for W plus, it covers a wider range, which is interesting. So it's sensitive to different, so smaller and higher axis. But yeah, so there is again additional difference between the two. So this is all at leading order. In addition to that, of course, at the LHC there is a lot of radiation, so higher order corrections are quite important. So for Draellian, they are order of 20%, and when the W is produced in association with a jet at high PT, in addition to this transverse polarization, it gets also longitudinal polarization, and yeah, so modeling of that becomes quite complicated. So just a short recap of what I just said. So to measure W mass, we need to model pretty accurately basically everything about the W boson. We need to model its rapidity, transverse momentum, and polarization. And everything depends actually on the flavor decomposition into all 6 flavors. So you need to control U from the C, and also U valence, so which is equivalently to U bar. Same for the D quarks. You need to control strange and the charm quark. Something which is, I believe, not discussed so much, but potentially this could be another effect. So here I assume that S and C quarks are just from the C, not intrinsic, and so some intrinsic strange, so SS bar asymmetry and intrinsic charm may play additional role in understanding of the W mass. And of course, so this is we have to model WPT somehow, and so the idea is to obtain this information from the data itself, from the Draellian neutral current and charge current data and the combination data. Okay, so now let's continue with actually experimental part of the talk, and we'll try to indicate how we perform these measurements at the LHC. And yeah, so here you see an example of event display. So this is early recorded by Atlas collaboration, the candidate of the W decaying into electron and neutrino. So what you see here clearly is energy deposit of the electron, which is in this particular event is the most straight track, so solar magnetic fields. That means it's a high PT track. On top of that, you can also reconstruct missing momentum. Okay, you see many soft tracks, so you see they are soft because they are curving quite a lot, and yeah, and in the colorimeter there is nothing essentially, and okay, so you can reconstruct missing momentum. Okay, so this is for the electron reconstruction. So for the muon, of course, you have a muon system which is outside, so it's different than Atlas and CMS, but it's quite easy to reconstruct high PT muons in both. And at the end, what you measure, you measure tracks of muons, and you measure them in the inner detector box in the muon system, and you match them together to perform particle identification. Yes, and as I said, missing energies from the so just mismatch of the energy in the colorimeter, or you can also use tracks for that. So you do that, and then you essentially apply some simple selection criteria to get your candidates. So the critical point here is to make sure that the events are selected online. So this is so-called trigger, and you cannot take all events. You have to take a subset of them, and the easiest way to get electrons and muons is isolated energy deposit, to get electrons, isolated energy deposit in the colorimeter. But on top of that, you require a certain energy threshold, which you have to do offline. Okay, on top of that, you need to, so this needs to be inside the detectors, in the central part of the detector in particular, and then these are eta cuts on the lepton. And all right, so for the Z reconstruction, we just require 2 electrons or 2 muons, and normally the trigger is, so if you require 2 objects, electron-like, it's suppressing background quite heavily already at this stage. If you require just a single, so with the very high luminosity which we have at the LHC now, it's actually difficult to take all the data. So you have to do additional cuts. And normal cuts are isolation with respect to the hadronic activity, so already at the trigger level. This is kind of unfortunate because there are actually interesting channels which you can study. For example, W produced within the jets. This is a different physics compared to what I'm talking about, but it's an interesting process. There are measurements of that from Atlas and CMS. So this is the electrolytic production of the vector bosons within jets. So these measurements are harder in this case, but also possible. Okay, and at the end, the electron or muon efficiency will be the leading systematics for the cross-section measurements, experimental systematics. And yeah, it mostly comes from this isolation requirement and modeling of it using different underlying event models in Monte Carlo. Okay, so events are reconstructed using colorimetry information for the electrons. Now, how do you at the end detect the Z boson? It's actually extremely easy. So you just reconstruct invariant mass for this lepton pair, and you see it's very clean signal after rather basic cuts on the quality of this clusters, so they're electromagnetic like. And okay, so of course you need to calibrate the energy, and this is actually done based on the known from lab Z mass. So if you compare Atlas and CMS, there is a similar performance. It's slightly more narrow in case of CMS. So it's okay. So there is a background, but it's almost negligible under the C peak. All right. So it's very nice, so that we know this energy very well since long time. So for the cross-section measurement, which applies requirements that the invariant mass should be between 66 and 116. A small miscalibration, if any, visible here, it doesn't matter. So it's a small effect. As I said, the biggest effect is efficiency, which needs to be understood. So this looks actually encouraging that you also may hope with large samples to improve the Z-mass measurement, not only W mass, but the Z-mass. But it turns out that this is actually, while experimentally it's easier, way easier, because you have both leptons reconstructed, it's actually at the end more difficult because all the calibrations are already using the Z-mass by itself. And so you have to introduce independent calibration and propagate back to the scales. So you have to do it totally, restart from scratch basically everything. Also, it's also not totally trivial from the modeling point of view because Z-line shape is not trivial in the standard model. You have next to leading order Letavik reaction, you have running widths, you have QED radiation, and all of that is in fact already in the calibration of the detector. So the combination of the calibration and modeling is very coupled in this process. Okay, so if you talk about muons, actually very simple, similar situation. So again, we have a well, easy reconstruction. So if you require muons detected in the muon system and with basic selection criteria, you get rid of all QCD background, and you have a very nice resolution, again slightly better for CMS compared to Atlas. Okay, so again for the W mass, the Z mass is heavily used to understand the energy scale, and yeah, and the same arguments hold. So if you want to measure the Z mass, which some people do with the muon channel, you have to calibrate on say shape side and understand all the modeling issues. Okay, so in case of W, there is another issue that since you reconstruct only a single lepton, there is a sizable contribution from the misreconstructed essentially dijet events from the so-called QCD background. So there are also Electron backgrounds related, say, WW production, but they are rather well modeled and they are small, so they are normally taken from the simulation. So the QCD background is yeah, the cross section for the jet production is very high, so you cannot really simulate it. So there are attempts, but it's almost impossible to get sufficient samples. So you have to do it to model the QCD background from the data. Again, there are for different measurements, there are different techniques, but generically, so normally you take a revert some set of selection criteria to enhance the contribution from the QCD background. For example, you reverse isolation requirements to enhance jets, and then you get a template, and then you do a fit. So you can do a dedicated control region, or you just, for example, fit a total ETMIS distribution. So this is shown here, and if you are from Atlas, you apply also ETMIS cut for the cross-section measurement. So you see a rather good description of the whole shape, but also you can also see that the background contribution is quite large, and it's also different for W plus compared to W minus in percent-wise. But in absolute, it's actually very similar. So it's one of the another handles to control it. That yeah. So W plus W minus production does care about the charge, but the background doesn't. Okay, and for Wms measurement, you can reduce this background further with tighter selection criteria. Okay, so again, few words on what are the actual measurements. What do they mean? So what do we actually at the end report in experimental papers? I believe you will have some more discussion on that in the following days. So it will be talks from John. And okay, so you know what's rivet, and so this is kind of connected. So basically what we have here is essentially fiducial cross-section measurement. So it's defined as follows. So we take a number of signal events and the total number of events. From that we subtract background. So this is our signal. Then we divide by luminosity, and then we correct for the efficiency in the fiducial volume. And if we want to extrapolate this cross-section to the total cross-section, then we also divide this fiducial cross-section by the acceptance. Yeah, formula is wrong, right? So I don't want from signal subtract background. I want to subtract from total background. Okay, it doesn't matter. So yeah, so the key issue here is the key point here is the definition of this fiducial cross-section. So we normally determine that from Monte Carlo, and so this is the ratio of the in Monte Carlo of number of reconstructed events with cuts and divided by number of generated events with cuts of the generated objects, so PT and E of the lepton. So the idea here that if you use fiducial cross-section for the theory predictions, they are closer to what we measure experimentally compared to the total cross-section, where we have a extrapolation, which is a purely model-dependent extrapolation. Okay, so fiducial cross-section started some time ago. Most of the LHC measurements use that, some not. And actually for Draellian, you can avoid using fiducial cross-sections. I will discuss that later in the talk. Right, so another issue is when you define this correction factor, so then you compute number of events at the generator level. So this after some fiducial cuts, you can use actually several different definitions with respect to QED radiation. So you can use so-called bare definitions. So essentially, this fiducial cuts are based on leptons only. So it's kind of relevant for dimuon situations. So muons in the detector are reconstructed as tracks, and whatever QED photon was present is normally not associated unless you do something special with that muon. Okay, so this is one case. So the other case, you can dress them. So you can combine the lepton with photons using certain clustering methods. So normally it's just a radius which is defined, and you integrate. So you combine the electron and the photon track. So this is most relevant for the electrons, because in the colorimeter, normally the QED radiation is rather, FSR QED radiation is rather collinear with the electron, and at the end you have a cluster which actually integrates the energy of both electron and photon. All right, and finally you can say, all right, so I know how in this Monte Carlo I can apply QED corrections and can look at the event record in the simulation and detect that this lepton was actually is before the final state QED radiation, which is normally generated by things like photos, or if it knows how to generate QED itself. But there is also in the event record, in the MCA event record, there is a lepton which is before the radiation. And then you can, in fact, apply QED radiative correction already at this stage. And so it's so-called born leptons. Okay, so it's all right. So the best is actually to report at least 2 levels. So the rest is preferred for follow-up phenomenological analysis because they are less model dependent. However, as I said, a lot of model dependence is already within the calibration of the detector. You cannot avoid model dependence in this analysis altogether. Born is quite useful for the phenomenological analysis which don't want to repeat electrolytic corrections. These are QCD fits in particular. They quite often use the Born definition. But okay, and sometimes, as I will talk in the following, you do want to correct to Born level during the measurements, which is a bit controversial, but could be useful. Okay, so now if you have a differential distribution which you want to observe, then there is another issue. It's not only, okay, so now you have to perform unfolding for the detector effects. Okay, so what we have, so if we are interested in determining a certain distribution for a certain quantity, for example, rapidity distribution, at the end, what we measure, we also measure the lepton pair rapidity. On the other hand, we have additional smearing effects because of the detector calibration or detector resolutions, actually. So the point here is, yeah, you have to solve this integral equation and yeah, determine the truth distribution from the measured. And the procedure is normally called unfolding. Okay, so for this unfolding, normally you need a transfer function, which is, you do need a transfer function, which is in most of the cases is determined from Monte Carlo, but okay, there are other methods which exist, so just have one reference. Then you have to do a bit of regularization. So this problem is actually ill-defined. So there are many solutions given the transfer function and observed reconstructed distributions to get the generated distribution. So essentially, you can always insert very rapid variation of the functions, or some delta functions here and there, which would be still valid solution for this equation. So the first regularization which comes normally is the binning discretization of this observed. So we bin the measured quantity, we also bin the unfolded quantity. So this turns out to be actually interesting for the phenomenological predictions as well. So if you go to starting from next to leading order, you have virtual contributions which are negative, and of course you have almost certain regions of phase space divergent real emissions, so they must cancel each other. And binning is one way to regularize predictions as well. So this becomes even more relevant for next to leading order. On the other hand, of course, it's very interesting to attempt some functional forms for unfolded results, and in fact, this is one of the areas in active development. So, on top of this binning, that you normally want to do other regularization, such as you want to make sure that the function which you get out is smooth. Yeah, so this is one way to regularize. The other way is to say that results should not differ too much from the prior definition. This is so-called biasing approach for the regularization. So these are used in many measurements. On the other hand, nowadays we also have a couple of unregularized results, which are essentially obtaining this truth beam distributions from profile likelihoods feeds to the data. Okay, so it's actually a lot of active developments. So there are many machine learning techniques which are used here. I mean, for example, if you want to measure some more complex quantities, you don't need at the reconstructed level to use the same variable. You can have different variables which may bring some additional information to reduce smearing effects. And so you can unfold multiple recall level variables into a single truth level variable. And yeah, and you can do it even in an unbinned way, since there's a few papers recently. Right. Okay, so if we talk about neutral current Draellian measurements, if we talk about repeated distribution of the pair, it's kind of not super relevant because the resolution is very good and whatever you do for unfolding is normally okay. Okay, so if we talk about Draellian measurements, which are production of ZW bosons and some of resonance production of dielectron pairs, so normally you deal with very many events, so large statistic samples, and so statistical uncertainties, you may want to use the full Poissonian approach, but on the other hand, if you have quite a few events, more than and normally we talk about millions of events, so it's quite easy to use just normal distribution, and just statistical uncertainty can be estimated. It's the square root of number of events effectively. You have to take care of the background subtraction, but otherwise it's pretty straightforward. So the key issue for these measurements are actually systematic uncertainties. All right, and systematic uncertainties are estimated based on the detector quantities, based on the detector performance, and based on the Monte Carlo modeling as well, in fact. And so essentially you normally have a central result and you vary certain parameters in the detector description, and you get an alternative result, and the difference between the two is the source of uncertainty. So there are two ways how one can deal with the systematic uncertainties. So using a so-called nuisance parameter representation, where for each source of uncertainty, you get a nuisance parameter which you fit in your profile likelihood function, and you have a penalty term. So in case of large number of events, you can use just a chi-square distribution, and so which is shown here. And the alternative is essentially minimized with respect to BJ and use the covariance matrix. So it's maybe an exercise for tonight to show the equivalence of these two representations. Okay, so this is well established, but okay, so there is also a care needed. So this gammas, the systematic uncertainties may behave differently. So if global normalization factors may cause some biases in the results, so you have to make sure that something is done. Right. So the other issue is how many sources of systematic uncertainties do you need to describe your measurement properly? And at the end, if you look at the recent LHC results, you quite often have hundreds of systematic uncertainty sources. And in fact, this is required to get an accurate description. Yeah, so they come from things like efficiency measurement or energy scale measurement. And normally each of the input sources is considered uncorrelated, or it's made uncorrelated, more or less, by constructing them that way. Still, many recent experiment measurements, within the measurement itself perform minimization of certain profile practical functions, so they reduce this additional systematic uncertainties. So, for example, if you have a background, you have uncertainty on the background, and you use a control region where you fit the background. And of course, in the control region, you have also systematic uncertainties, which are also relevant for the signal. And all of them, it's not only the background normalization uncertainty, which is reduced, but also all our systematic uncertainties, if you do it properly. So this actually correlates the sources, so you have to treat this properly. Also, if you do a combination of the channels, there is a quite sizable profiling of systematics, and you have to deal with that. Okay, so this is a side remark on the measurement techniques. Okay, so as I said, it's actually, yeah, so for the Draellian production, it's very nice that there is an ability to measure in two leptonic channels, electrons and muons. And at the end, it provides a very interesting cross-check of the consistency of the results at the sub% level sometimes. And so this is actually summarized here. So the ratio of the fiducial cross-sections for the Z boson compared to the W produced in the electron and muon channel. And so this provides you a lepton universality check. All right. So of course, in the standard model, everything should be at unity, and experimentally we know that very well from lab for the Z boson. For the W, in fact, again, this limited statistics for lab 2 means that the uncertainty is quite large for directly produced Ws, but there are, on the other hand, measurements of, say, tau decays, Keon decays, and pion decays, which indirectly can probe this lepton universality very accurately. But still, if you compare this to this recent Atlas result, we see that it becomes interesting test to the lepton universality. It's not only cross-check, but an interesting test of this quantity. And okay, so up to now, up to recently, it was mostly considered as a cross-check of what's going on. But given a couple of years of anomalies observed in the B decays, so where people start to see indications of lepton universality violations for so flavor changing neutral current processes with involving P2K LL. So there are differences in electrons to muons at almost 20% level. So this type of checks become actually very interesting. So it's very hard to imagine a sizable lepton flavor universality violation at the Z or W peak, because here we see that the resonance contribution from new particles is suppressed. But if we measure Draellian production at high masses, it's actually very interesting. And in fact, there are relations of some models which describe the Z B anomalies with additional Z primes or leptic ones, which predict a sizable effect for the high mass Draellian. Okay, all right. So let's continue with our precision Draellian measurements. And yeah, so one of the most accurate results, this is this Atlas result from a couple of years ago, related to the measurement of the WZ cross-section as a function of pseudo-rapidity for the leptons, or the rapidity of the lepton pair for the Z, for double and for the Z boson. So okay, it's performed an electron and muon channel, and this provides you a very nice cross-check of the consistency of the two. So if you perform a combination, you get, including also systematics, you get at the end chi-square which is close to unity with very high p-value, and the accuracy of the combined result is actually better than 0.5%. So okay, this is all illustrated here, so it's a very nice consistency between the measurements, and all right, and then you see that the W plus is indeed larger than the W minus, and yes, and the Z, yeah. All right. So now, okay, so you now want to do a bit of phenomenology. So you want to see how these measurements can be used to control your PDF uncertainties. So this is what we aim when we want to go for the WMS measurement. Okay, and so what you can do, you can take this atlas data, combined atlas data, which is having better than 0.5% accuracy, excluding the luminosity uncertainty, which is order of 2%. And then we can try to perform a fit next to leading order QCD plus next to leading order rhetoric using XFitter as this is a program which allows you to perform the whole package, essentially evaluation, convolution to compute cross sections, and the likelihood calculation between the data and predictions. So you do that, and you observe that in fact the chi-square is not super good. So it's quite bad actually. P-value is very low. So okay, we don't want to say there is new physics in that, but it looks like this description is insufficient. You can see that potentially with varying the scales for the prediction, one can improve, but still it's quite poor. And okay, so the key point here is that we need to do either something with the modeling, or we want to modify the measurement such that it will be easier to fit with fixed order predictions. All right. So, okay. So the key point that the measurement is fiducial, so it performs with PT cut on the lepton and okay, missing energy cut on for the double, and also eta cuts on the leptons. Right. So if we do that, we effectively actually shape the PT distribution of the W or Z boson. So the acceptance of this, so the efficiency of this cut as a function of the PT W or Z is actually not flat. That means we shape this distribution, and of course, if we talk about fixed order predictions, as you learned before, they are only accurate enough if you integrate over PT. So at low PT, you cannot predict, you need to do something else. So, for example, you can do resummation. So also, there are some theoretical issues. For example, if you compare predictions based on different formally same order programs like Fuse and Dividing Law, there are sizable 1% level differences. In fact, this is traced back, it's understood recently. We can discuss it in the evening, what's going on here. And all right, so if you add the resummation, you in principle can correct for this, because then you model the PT distribution. You may model much better the PT distribution. And so if you just look at the effect of the resummation, let's start from the next to leading order prediction. So in this case, next to leading clock resummation changes, so there's quite sizable change of the prediction. and it's different for W plus compared to W minus compared to the Z boson. On the other hand, if you go to next leading order, the difference becomes smaller but still sizable. So the point is accuracy is 0.5%, and right, and so this type of correction needs to be done. So this is one way. The other way will be, I guess, we can. Okay, so I think I will leave the other way for tomorrow. So we will continue with this problem. So we have an issue that we have a difficulty to describe simplest measurement performed in rapidity in invariant mass using fiducial phase space using fixed order predictions, and then we'll see how to improve on that with a different way to perform the measurement. Okay, so I'm stopping here.
Excuse me, Frank. You
I
are
hear you.
very, very faint. Maybe if you put your microphone closer to your mouth.
Okay, yeah, it seems like Zoom has auto-adjusted my microphone volume again to the too low a level. I hope it's better now.
That's much better.
Yes.
Okay, thanks for pointing that out. And I was just saying apologies that you didn't get a proper introduction at the start, because just when I started the recording, my Zoom had crashed, and when I came back, you were already going with your talks. I didn't want to interrupt. So thank you very much, Sasha, for this introduction to experimental results and also many results related to QCD and strong interaction effects from the LHC. As you say, it's a big task to ask someone to give a summary of experimental results from the LHC. So thank you very much that you stepped up to that challenge. And I think we have maybe 1 minute for some immediate questions now, and otherwise we can also probably take questions either during the recitation session if you're joining in the evening, or in the second lecture tomorrow. But let's see if there are any quick questions from anyone now. Feel free to raise your hand or talk directly, or write in the chat if you can't talk. I don't see any questions yet. Sasha, do you already know whether you would be available for the recitation session in the evening?
Yes, I can join. We'll see.
Okay, cool. So we can also come back with any questions. Some you already indicated along the way that we can discuss tonight.
Mm-hmm.
Cool. Then thank you very much. I'll stop the recording, and in case I crash out, I'm already saying goodbye to everyone now. And have a good lunch break, and see you again in the afternoon at 2 p.m. in Central Europe, or later on for the tutorials or recitation session. And the sun is coming out, right?
All right.
See you later. Thanks, Sasha.
Bye. Thanks.